Okay, so in this next segment, I am going to describe context-free grammars, which are a very important formalism used within the parsing problem. So I'll first give a formal definition. And one thing I should note is that context-free grammars are not only used in linguistics, they're also of central importance in computer science, both in theoretical computer science and also in programming languages where they play a very, very important role. Okay, so a context-free grammar has the following components. So a context-free grammar G is a four-tuple consisting of n, sigma, r, and s, where we have the following elements of this tuple. So n is going to be a finite set of what we call non-terminal symbols. Sigma is going to be a finite set of what are called terminal symbols. R is a set of rules. Come back to this in a second. And finally, S is some member of N, which is referred to as a distinguished or start symbol in the grammar. So each of these rules takes the following form. We have something on the left-hand side of the rule, X. X has to be a non-terminal. And then on the right-hand side of the rule, we have a sequence of items, y1 through yn, where each of these y's can either be a non-terminal n, or it can be an element of sigma. Notice that n could be 0, so actually this right-hand side of the rule could just be what we often write as epsilon, which is the empty sequence of length 0. So that's a very abstract definition. Let me give you a concrete example. So here is an extremely simple grammar for English, but it is useful in illustrating the definition that I just showed you. So I have the four elements of the context-free grammar here, n, s, sigma, and r. So n in this case, as I said, is a finite set of what are called non-terminals. So we have symbols like s, np, vp that you've seen appearing in those parse trees I showed you earlier. And notice we also have parts of speech, things like dt, vi, vt, nn, in. These are actually going to be parts of speech in the grammar. The distinguished start symbol is simply going to be s. Okay? And then finally, we have a set of words in the language. So sigma might consist of the following set of words. So we have very small vocabulary here. Moristic grammar would have a much, much larger vocabulary. And finally, we have a set of rules, okay? So here are the rules in this particular example grammar, and as I said, on the left-hand side of the rule, I always see a non-terminal, for example, S, VP, or NP, or PP, and so on. And on the right-hand side of each rule, I see a sequence of 0 or more symbols, where each symbol could be any element of N or sigma. So in particular, I have S goes to NP, VP here. If VP goes to VI, VP goes to VTNP, and so on and so on. Over here I have rules where actually the left-hand side is a single symbol, for example VI, and the right-hand side is a word, for example sleeps. So this is one simple example grammar. Later in the class we'll talk a lot more about what these different symbols mean, but just briefly, S basically stands for a sentence, VP is an abbreviation for a verb phrase, NP is a noun phrase, PP is a prepositional phrase, and so on and so on. So that's a formal definition of context-free grammars, and also an example of a particular context-free grammar. The next crucial concept is going to be the idea of a derivation, or more specifically what's called a leftmost derivation. So a derivation is a sequence of strings, S1 through Sn, where this sequence of strings has the following property. So S1 has to be equal to S, this distinguished start symbol in the grammar. Sn has to be made up of elements of sigma alone. So sigma star is just the set of all possible strings, which can be derived from sigma. So if I have sigma is the dog A, then sigma star includes strings like just the empty string epsilon, A, dog, there, two-word strings like a dog, the dog, and so on. Basically, any string you can form through a finite sequence of these words in sigma, where we also include the empty string sigma, epsilon. Okay, so Sn has got to be a sentence, for example, the man sleeps, only elements of sigma. And then each intermediate Si, for I equals 2 to n, is derived from Si minus 1 by picking the leftmost non-terminal x in Si minus 1 and replacing it by some beta, where x goes to beta is a rule in R. So here's an example of a derivation, and actually I'll go over this example in much more detail on the next slide. So we start off with S, that's the first string. The next string in this derivation is NPVP, and that's because I've taken S and replaced it by NPVP. And then I take this NP and replace it by DN, and so on and so on. Let me actually go to an example where I'll illustrate this a little bit more carefully. Okay, so we always start in a derivation with this distinguished start symbol, for example S. And then at each step, we're going to choose some rule under the grammar. So we might, for example, choose S goes to NPVP. And in this case, we replace S with the right-hand side of this rule, the NP goes to VP. So the critical idea in a derivation is that at each point, we take the leftmost non-terminal in the current string, and we find some rule where that non-terminal rewrites as a sequence of non-terminals, and we simply replace it. So the next non-terminal we're going to modify is NP. So we pick some rule from the grammar. For example, NP goes to determinant n, replace NP with determinant n, and now we have the sequence determinant n VP. Again, I pick the leftmost element, dt in this case. I pick some rule. In this case, dt goes to there. And now I have the n VP. And we can keep going like this. And finally, we end up with a sequence of words. Okay, so a complete derivation always ends up with a string where every word in that string is a word in the language, i.e. every element in this string is a member of sigma. Okay, so the context-free grammar will define a set of valid derivations where any derivation is valid if it starts with S, ends with some sequence of words, and goes through this process where at every point we replace the leftmost non-terminal using some rule in the context-free grammar. It's very useful to represent these derivations as parse trees. So this parse tree, which I've shown you here, is nothing more than a representation of the derivation. So we have S at the very root of the tree. Notice we've chosen S goes to NPVP as the first rule, and that's reflected with the fact we have S dominating NP followed by VP. Similarly, we have NP dominating determinant noun because that was the next rule we showed here. And so you can go through each of these rules used and see that it corresponds to some subfragment within this tree. Okay, so given a context-free grammar, we have a set of valid derivations under the grammar. And this set can be infinite. In fact, in almost all interesting cases, it's going to be an infinite set of possible derivations. So a couple more definitions, or one more definition. So we say a string S, so a sentence, so this could, for example, be the dog laughs. We say a string S is in the language defined by the CFG if there is at least one derivation that yields S. Okay, so a CFG defines a language. A language is a set of strings, and a string is in the language if there's at least one parse tree for the string. Critically, a very interesting property is that some strings in the language may actually have more than one possible derivation. And this leads directly to the problem of ambiguity. Let me give you an example of this. So here's a very simple sentence. He drove down the street in the car. And here I have one possible parse tree for this particular sentence. But under most grammars for English, there will also be a second possible parse tree, which I've shown you here. So let's go back and forth between these two. So in this particular parse tree, this prepositional phrase is seen lower in the tree. And in particular, I have a rule NP goes to NP prepositional phrase at this low level in the tree. Whereas if I go back to the previous parse tree, you'll see again we have this prepositional phrase in the car, but it's a little higher in the tree. And in particular, we have a rule VP goes to VP prepositional phrase. So basically, there is some ambiguity about whether this prepositional phrase is seen high in the tree, attaching to this VP, or if it's seen lower in the tree, attaching to the noun phrase down here. And that actually corresponds to two different possible interpretations of this sentence. So under this parse tree, in the car is modifying this entire verb phrase down the street. And this basically corresponds to by far the most likely interpretation, which is that I'm doing the driving in the car. Let's look at the second parse tree, though. In this case, we have in the car modifying street. And so there is a possible, although highly implausible interpretation, where the street that I'm driving down is actually located in the car. So I have a street in the car. You could imagine some crazy world where that could happen. And that's what this attachment corresponds to. This is where the prepositional phrase in the car modifies street, and so we have a street in the car. So, just to recap, critically, with an underlying context-free grammar, you may find that there are multiple derivations for a particular sentence. And those multiple derivations very often correspond to different interpretations of the underlying sentence.